Okay,
Yes.
yeah. I
Okay,
was not
better,
showing
better.
the right screen.
Okay. Thank you so much, Dr. Charlie Lohan. So this is Dr. Charlie Lohan. He did his PhD at Toulouse INP, and now he's a machine learning engineer at NVIDIA. So please, round of applause for the presentation. Now the floor is yours, Charlie. Thank you.
All right. Thank you so much for the introduction. So yeah. So yeah, I'm a software engineer in the PhysicsNeMo team at NVIDIA. So basically what we do is that the goal of our team, so we develop PhysicsNeMo, that's one of our goals. So PhysicsNeMo is basically a library for basically for AI for science, or basically any kind of engineering application. And I will only, so we have a lot of things. So there are a lot of things related to what we call CAE. So CAE is everything under engineering, like mechanical and aerospace engineering, all those type of things. And we have another side of the project that is more focusing on weather and climate. So I will not be talking about the weather and climate stuff today at all, even though that's one of our main activities. So yeah, just the session will be divided into 3 parts. Yeah, so first part will be like very general, probably just 30 minutes should be fine. It's just some slides. And I will try to explain what is PhysicsNeMo, what we are trying to achieve with PhysicsNeMo, and so on. So it's basically an introduction to PhysicsNeMo. Then I will go to code deep dive. Actually, it's not going to be coding at all. I don't know why I wrote code deep dive. So I'll go into some kind of theory about the type of graph neural network that we have in PhysicsNeMo that are called mesh graph net. So it's a type of a it's basically to handle complex geometries. So it's an architecture to train surrogates that can handle complex geometries like those you can find in almost any engineering application. And then in the last third of the session, so we'll do a little bit of coding, and we'll try. I haven't tried actually, so to be a kind of live exercise even for myself. So we'll try to code a Lagrangian mesh graph net. So yeah, we'll go into that later. Yeah, so we all know simulations are critical for any engineering problem. And actually if we go back a little bit in time, this started like if we go back to like the 60s or 70s, actually simulation was not used at all, right? They were doing a bunch of experiments, even like, and they were doing like those basically those scaling laws, and that's how they designed the space shuttle basically. Then when computers started to become more powerful, you started to see more of numerical simulations. And they did not, so something interesting actually is that you might think that they replaced those experiments, but actually that's not true. If you go to, let's say, to an aircraft engine manufacturer, they still do those kind of experiments. So it's not the same experiment you might be doing in university, right? They build an actual engine and they do some kind of yeah, they put some tooling on the engine to do some measurements, but those are kind of large-scale experiments. They still do all those testing and experiments. So simulations did not replace experiments. And why I'm saying that is because nowadays there are a lot of people saying like AI will replace simulation, but that's just not true. It's the same transition, right? AI will just complement both experiments and simulation, traditional simulation. It's not going to replace any of those, because all those 3 things they basically need each other. So why we need AI is because we're kind of hitting a limit in terms of simulation, at least in the opinion of many people, is that usually we can do like for complex industrial system, we can do like one simulation, maybe a couple of them. But we have limitations in terms of simulation run, so the number of designs you can test, and also in terms of the complexity of physics you can capture. So, like, for example, people who do CFD, you need models because you can't resolve all the turbulence scale in any kind of turbulent flow. So simulations are actually limited in terms of what they can resolve. And there is a third thing, maybe is the latency. So it's like there are some specific applications actually. So I don't know too much about optimal control. Actually, I know the lectures about optimal control, but I don't know too much about it. I'm not really working on this directly. I'm more working on PDs. And yeah, in optimal, when you need to do like a control of an actual system, you need very high latency. So very low latency, sorry. So that's why like AI surrogates can actually replace simulations in this case because they are very fast for inference. So it's all about basically accelerating simulations because we want to increase the number of designs we can explore and we want to have lower latency and all those things. So at NVIDIA, we have two ways to accelerate simulation. The first way is actually to take your traditional PD solver and to accelerate it with what we call the CUDA-X libraries. So there are really a lot of libraries, and so there is CUDA, but actually CUDA is not something you should be using unless you intend to work at NVIDIA. You should be using mostly more high-level APIs to CUDA. So for example, there is Warp that you can use. So it's purely Python you can use to write CUDA kernels. You have PyCUDA, and you have Qt, QSolver, QOPT. There are a lot of libraries for specific type of scientific problems, and all of those actually have Python interface, such that actually as a user you never need to go into like C++ CUDA. So the recommended entry point is actually to use those Python bindings to C++ CUDA. So that's the first way to accelerate simulations, is to basically to port them to GPUs. The second way is to go for AI models, and that's where PhysicsNeMo is. So you, instead of running the same solver, you will basically replace the simulation by some AI surrogates, some machine learning surrogates. So there is PhysicsNeMo, is just one of them. There is BioNeMo, which is more focusing on biology problem. And there's Earth-2 Studio, which is something sitting on top of PhysicsNeMo, which is only for weather and climate application. So there are also a bunch of applications there. So this is basically some performance measurement of some different engineering problems. So we have three engineering problems. The first one is an external aerodynamics. I think it's the RAND simulation of a car. The second one is a data center cooling. So it's basically it's also a CFD simulation of an entire data center, and the quantity of interest is the temperature field and all those things. And the third one is reservoir simulation, which is a kind of CFD problem for in the context of oil and gas exploration. So it's basically to compute the flow in the porous medium to see how the reservoir are evolving, if there's, and basically where you need to dig, where you need to inject maybe some water to push out the oil or the gas and all those things. And so the baseline for all of them is a classical CPU-based solver. Then the light green is the same solver but ported to GPU. So we see that if we take the RAND solver, we port to GPU, we have a speed of times X. For data center cooling, we have a speed of times 8, and for the reservoir simulation, we have a speed of times 40. And the dark green is actually when you replace this with an AI surrogate, and we see that this is not an order of magnitude faster. It's 3 orders of magnitude faster than just porting to GPU. Doesn't mean it will be accurate, but it's much faster. Yeah, and it's not a small improvement. Yeah, so then try to give you a kind of overview or breakdown. Oh, there's a question already. How do I? Can you
hear me?
Yeah, I can hear you. Yeah.
It's just a very starting warming question. So in the previous slide, you show the speed ups. Is there any intuition why the reservoir speed up with the AI is much less than the other ones?
Yeah. Actually, it's because it's like it's not like one neural network. It's an entire pipeline. So it is actually a very complex application. It's not just just training on your network and doing inference. It's like you have basically a domain which is a representation of the subsurface, and you need to do data assimilation, right? Because you have some measurements, but you don't know what is underground. Okay. So you need to do data assimilation. So that's basically one neural network that does that. So this is basically the inverse problem, if you will. And once you can infer what is under what is in the subsurface model, like how is the reservoir state, there is a forward problem to solve, which is another neural network. So I am not super familiar with this example. Actually, it's I don't think it's open sourced. This is for an industry customer, but the idea is that this is a very complex workflow, and some parts of it were pretty not optimized. So like it's easy to optimize, like one big neural network, but when you have like 5 or 6 neural networks and they need to kind of interoperate and exchange input and outputs, it becomes kind of a mess. So yeah, that's what happened there. But this doesn't mean it's the optimal, right? There is still probably some opportunities to optimize it, and the speed up will be higher. Did I answer the question?
Yeah, you did. Thank you very much. It's interesting to know because we're trying to kind of train our own AIs for problems and investigating the type of stuff that you're going to present today. And it's nice to have this intuition where situations might be harder for optimizing, depending on the complexity of the problem.
Yeah, and something else is that so I'm not totally sure about how those things are optimized. For some I know, but like this one I don't know. So for instance, it's possible, like, they did some very simple optimization on this, like didn't go, like you can do some stuff like you can always optimize. Optimization is like a never-ending process, right? You can fuse the layers, you can go to lower precision, you can do a bunch of stuff there. And I'm not sure they went that far. Oh, sorry. I'm not sure they went that far in this application. So this 79 there is most likely not the optimal. For those, I know there was a lot of work put into accelerating those. Yeah.
Fair point. Thank you.
Yeah. So that is the overview of PhysicsNeMo. So really, like, actually a lot of users that I interact with, especially users from universities, they are kind of confused about what is PhysicsNeMo. They know it's there, they know it exists, but they don't know what it's used for. And a lot of people actually think it's to replace PyTorch. So there is nothing that is more wrong than this. PhysicsNeMo is not to replace PyTorch at all. We're not at the scale of PyTorch, right? We have only 10 engineers in the team, so we're not replacing PyTorch. So it's actually something that sits on top of PyTorch. And there are some other components that are not PyTorch. And this is like what you see there. This is the lower level stack. Okay, so a big bunch of this lower level stack is actually PyTorch. So basically, we'll have we are going to use PyTorch to define some models. So one big component of PhysicsNeMo is actually this model architecture. It's what we call the model zoo. So we have a lot of them, probably more than 50 for different types of problems. And those, they will basically use PyTorch, right? They will be implemented in PyTorch, and some of them will use also some more like customized CUDA operation in Warp. So Warp is not PyTorch; it's something also in the lower level stack. But you can see it like it's at the same level of PyTorch, but it's not PyTorch, and it's differentiable, right? It's more like a kind of JAX, but with more flexibility. And then there's DALI, which is a NVIDIA library for optimized data pipes. So data pipes is also one other big thing, is that we have some data pipes that are optimized for GPU computing. And we have a bunch of the data pipes. Some are very specific, some data sets, and some are more like specific, some kind of modalities. For example, we have a data pipe for kind of mesh simulation. We have those things. So those are two of the major components in PhysicsNeMo. And all of those there, they sit on top of PyTorch. They can fully interpret with PyTorch. That means if you want to define your own model, this is fine. It's just another PyTorch model. The same way as PhysicsNeMo models are just other PyTorch models, but with some optimizations. And another big component of PhysicsNeMo is what we call the train recipes. So it's basically a bunch of examples. And there are a lot of examples, and people are not always clear about what are those examples. So the train recipes is because, at least when I was a grad student and I read a paper, I'm like, yeah, that's very nice, but I want to see the source code. Then I will go to I will find the link to the GitHub repo. I'll go to the GitHub repo of this paper, and I will just copy paste the source code. And either I use it or maybe I just read it. If I need to use it, I will copy paste it. So you need to have access to the source code for different papers or different applications, and that's exactly what those train recipes are. Some of the train recipes are actually the source code associated to some papers coming out of NVIDIA, right? So instead of going to some random repo, like where you have like one application, instead of this, they go into those train recipes. And usually the train recipes, they are designed in a way that they are quite easy to understand and easy to customize. So if you need to do, oh yeah, like a CFD application, you go to check out the train recipes in the CFD section, you'll take one, and maybe you just read it, maybe you copy paste it and customize it. So that's the way they're supposed to be used. So yeah, those are kind of reference sample applications. Yeah. Yeah, so this is just an overview of what we have in the model zoo. So I say we have a lot of architectures there. There are a lot of fully data-driven models, like we have Domino, we have all the neural operators, we have DeepNets, we have FNOs, we have we have the Pinot, the physics-informed neural operator. So a lot of stuff that we do is physics-informed. So that means we have some kind of a physical constraint or physical losses. Not everything. Some are fully data-driven, but most of them support some kind of PD-based information or PD residual information. And we have everything related to different models. And we have a bunch of other models that are more like domain-specific or application-specific, like in particular for weather and climate. So yeah, the main feature of PhysicsNeMo is built on top of PyTorch. It can fully interpret with PyTorch. It's more like a complement to PyTorch rather than a replacement. Everything at some level, everything we have in PhysicsNeMo has some level of optimization, whether it's some kernel fusion, some compilation. We have a big package for distributed training with domain parallelism. Then there is of course, like what I mentioned just before, the model zoo. We have kind of the zoo for data pipes, which is kind of the same as models, but on the data pipe side. So different data pipes to load different data sets or different data modalities. Then we have those kind of lower level geometry module, because one of our main targets are actually the complex geometries, and many of those models you see there actually has some very specific operations to handle complex geometries. And for this, we have this geometry module with utilities like for SDF, sign distance function. We have I think we have some kind of cube marching algorithm, some modules to handle the point clouds to get the nearest neighbor. So it's really like some kind of lower level geometry utilities. And if you want to build like an application where you need to say, let's say you want to resolve the flow around an aircraft, so some kind of aerodynamics problem, and you want to build your application from scratch, you would probably need to reuse those optimized geometry, those optimized utilities from the geometry module to be able to handle the geometry. And finally, we have those things for physics informed training. Yeah, so this is just this is a kind of sample of all the applications that we work on. So there are a bunch of links. So I don't update the like the GitHub repo for the session, but I will do it, and I will put this those slides inside. So you'll have all those links later, and you can go to check out the links if you want to. Yeah, so now I will go a bit more into CA applications. So basically application for engineering domain. Let me see. What time is it? Okay, it's been 15 minutes. Yeah, so one of our big application is actually yeah, there is a question.
Hey, I have a question real quick.
Yeah.
You mentioned the bio NEMO,
Mhm.
and I saw, I think it was a LinkedIn post, right? They used for like drug development or something like that. Is the bio NEMO kind of can it communicate with PhysicsNeMo in the sense that like calculate forces or something like that?
No. It's a different library. Yeah.
Okay.
I'm not saying that you cannot like use them together in the same application, because at the end of the day, they are both PyTorch, right? They are both some stuff sitting on top of PyTorch, but like PhysicsNeMo is more for CAE and weather, and BioNeMo is for biology. Yeah.
Okay.
So yeah, I actually have never used the same together in the same application, but I assume it's possible.
Okay. Thank you.
Yeah. Okay. So yeah, this is what I explained before: experiment, simulation, surrogates. So now we are moving to kind of like surrogates that can complement simulations, but not replace simulation. Yeah. So yeah, so car aerodynamics is one of the main application, and more to be more specific, kind of you can see that as a digital twin of a wind tunnel for a car. So instead of like doing your like let's say you change the geometry of the car, you change the inflow, that all the kind of stuff people like car manufacturers would want to test in an actual wind tunnel. We have basically a digital twin where they can test this in a virtual environment, right? And yeah, the goals are what I explained before. Is to explore a larger design space, to perform sensitive analysis and inverse design, so kind of shape optimization, those type of things. And also, yeah, something I didn't mention before is that if you run a wind tunnel, okay, let's say you want to do like an actual simulation of your car. Like let's say you want to do an LES simulation or something like this. If you run a wind tunnel, you're going to have some measurements, but there is no way you can use this like to inform your simulation, right? If you use a virtual wind tunnel, you get your output velocity fields around the car, and actually you can use those to initialize a new simulation. And actually we showed that this brings a lot of speed up to the simulation by initializing with say initial solution coming from an AI surrogate. So that actually enables some kind of hybrid approaches where you can have an AI surrogate that informs an actual simulation that's going to speed up the simulation and increase its accuracy. So that's one application where AI and traditional solvers can actually work together. Oh yeah, so that's a video.
Everything manufactured.
Do you have the sound of video or not?
Everything
Yeah.
Oh, okay, good.
manufactured is first simulated with advanced physics and solvers. Computational fluid dynamic simulations, or CFD, can take hours or months. limiting the number of possible design explorations. With an NVIDIA Omniverse blueprint for real-time physics digital twins, software makers can integrate NVIDIA acceleration libraries, PhysicsML, and RTX visualization into their existing tools, enabling a 1200x speedup in design iteration time. Here, Luminary Cloud builds a fully real-time virtual wind tunnel based on the blueprint. First, Luminary uses the NVIDIA Modulus PhysicsML framework to train a simulation AI model using data generated from their NVIDIA CUDA-X accelerated CFD solver. The model understands the complex relationship between airflow fields and varying car geometries, generating results orders of magnitude times faster than with the solver alone. The AI output is visualized in real time using Omniverse APIs. Now an engineer can make geometry or scene modifications, seeing the effects in real time. And because of Omniverse's data interoperability, the engineer can even bring new geometries, and the simulation will adapt instantly. What took weeks or even months is now a matter of seconds. Software developers everywhere can now bring unprecedented speed and flexibility to the world's industrial designers and engineers, helping save massive costs and shorten the time to market.
All right, so actually they mentioned Modulus. Modulus is the old name of PhysicsNeMo. It used to be called Modulus like a year ago or so. Yeah, there is a question again.
Yeah, just super fast. It talks about, and you mentioned using those accelerated simulations to help make decisions, right? Like design of the cars or any other decision you might have. Are those more ad hocly helping someone else that is making a decision and a human decision, like a human gradient descent, or is there an automated way to connect both the simulator and a search algorithm in such a sense, right? Either derivative free, or I would be more interested if there's a way to backpropagate gradients throughout these models.
So I'm not sure I totally understand the question. So your question, okay, you have this AI surrogate, can give prediction very fast. So your question is whether we can backpropagate the gradients through surrogate to do, let's say, design optimization or something like this, or is it something more like you think there will be like kind of of agent that can interpret basically the output of the simulations and
yeah.
So
my question, if it's this gradient-free method that would be more ad hoc, either an agent or any other Bayesian optimization style where you're kind of like approximating without actually looking at the gradients of the simulation itself.
Yeah, that's an interesting question. So we don't do that in our team. And I don't think there is anyone at NVIDIA doing that, because that's not really our job, right? But we have partners, like I know some startups. They basically do so they do like some kind of chip design, for instance, or could be other systems, but I know some in chip design. So for instance, they would have an agent. So I think it's basically an LLM, and they have this kind of AI surrogate. So it could be a PhysicsNeMo surrogate, and so they will compute very fast some quantity of interest, and they'll use basically reinforcement learning to teach the LLM, oh, this is a good design solution, this is a bad design solution, right? And so I think it's possible, but it's like a much broader scale than what we do in our team. In our team, we are only focusing on the AI surrogates. So, but I think that's I think that's a very good question. And if you have an idea to make a startup, I think that's a very good thing to do. But I know there are people trying to do that nowadays. Yeah, so it's a kind of it's like a gradient free, right? In reinforcement learning, you don't need to backpropagate through the entire actually you could backpropagate through the entire simulation, because as an AI surrogate, the simulation is actually differentiable, fully differentiable. So you could use the backpropagation through it. But it's more like looking at the quantity of interest and training an agent with reinforcement learning to say, yeah, to kind of guide the design decision. Yeah.
That makes sense. Thank
Yeah.
you.
There's also some, so actually all those applications, so this kind of a car aerodynamics thing, it's actually fully open sourced, the entire application. So even the wind tunnel visualization, and there is connection. So there is even a data series and everything to basically deploy it in the cloud, and everything's open sourced. So those you'll not find those in PhysicsNeMo, but it's what we call the blueprints, the Omniverse blueprint. So Omniverse is an NVIDIA library for basically for a lot of things, for robotics, for rendering. So yeah, like all those kind of rendering, actually, they are just purely in Python. So you have access to accelerated ray tracing or Gaussian splatting, all those things in Omniverse. So it's to build some kind of digital interactive environment, and those can ingest. They can ingest output of simulations or basically anything. They can ingest anything that describe a 3D scene. Yeah. But those go beyond what PhysicsNeMo is. Those are that's why we call it blueprint. It's more like taking a lot of pieces of software together and building an entire application.
So one quick question on this. The Omniverse, how does it connect with the PhysicsNeMo? Do they provide you with the equations, like in a rigid body dynamics of a robot, right? Do they provide you with the PDE and then you start from there?
No. So Omniverse is not based on PDs at all. Omniverse, you can see that as a set of accelerated components for interactive virtual environment, right? So that's why I mentioned robotics. So in robotics, you need like a physics simulator, and this would be either Warp or Newton, which are actual physics simulator for robotics. Omniverse is not in itself a simulation engine, but it has some interface to Warp, so you can use Warp in Omniverse. But this uses more like so this example you see there uses actually more like the rendering capabilities of Omniverse. So the simulation is performed with PhysicsNeMo. Okay, so the way you can see Omniverse is that there is some kind of physics engine, whatever it is, could be a black box thing, and it gives you a bunch of let's say, actually there could be multiple physics engine, and it gives you access to a bunch of rendering, of accelerated rendering functionalities. So Omniverse just takes those two things. So in that case, the physics engine is PhysicsNeMo, but you could think of something where you have PhysicsNeMo for, let's say, one asset, for maybe, let's say, some part of a robot, and maybe Warp or Newton for other assets, for other part of the environment. And you just ingest all those things into Omniverse, and you can use the rendering capabilities of Omniverse, and you can render basically like 3D environment of the interaction between those things. I'm not sure it's very clear what I explained. Is it clear?
Yeah, it is. It is. I still have many questions then once I want to try to implement it, but it's very clear what are the abstract steps to do it.
Okay, yeah. So for Omniverse, yeah, the entry point for anyone to use those type of things is the blueprints. So those are fully open sourced. There is actually something also, is what we call the NEM. So it's basically the blueprint that is deployed by NVIDIA. So it's not like a full functionality NEM, but you can, for example, you can change the geometry. So you can play with it. I think you'll have the link there. I'm not going to go there now, but you will have the link for it in the slides. It's basically, there is a web user interface, and you can change the geometry of the car, not everything, but some parameters. You can change the airflow and everything, and it's going to do inference for you of the flow prediction. Yeah. So it's kind of blueprint deployed in the cloud already. It's more to play, right? You can't You can't customize it. To customize it, you need to go to the source code and start from there. Yeah. Okay. So now, in terms of like, if we go back to this core aerodynamics example, we need. So there are some challenges. The challenge in terms of AI surrogate is that one of the main challenges that if you do when you do simulation, your number of degrees of freedom will be from the tens of millions to the hundreds of millions, right? So this would be a number of cells in your mesh, right? And the reason why you need those, because like in this case, you need to resolve the boundary layers, you need to resolve like the very small geometrical details around the wheels, around the mirrors, which are actually causing a lot of drag. So they are actually absolutely critical to resolve correctly. And just scaling to those huge number of degrees of freedom in an AI surrogate is actually a challenge, right? So, and here you can see something else that they use adaptive refinement. So the mesh is obviously finer in those regions and coarser far away. And this is also another challenge especially in machine learning models for those applications. And so there is other things that most models, they actually, if you look at CNNs, if you look at a graph neural network, they're actually very good for local interactions, to capture local interactions, but they're not that good to capture longer scale interactions. Oh, then you could say, okay, let's use a transformer, but then transformer is the opposite. It's very good for long scale, long range interactions that you will have in this type of flow, but it's not as good for local interactions. So because those physical phenomena are multi-scale, so you need something that can do both at the same time, both long range and small range. Another challenge is that most of those models, they will not generalize to new architecture. To new geometries. You'll train it on 4 or 5 geometries, and then that's it. It will not generalize if you change something. So a lot of work that we put into those CA models is actually to solve all those changes, to be able to scale, to be able to handle different scales. So to be able to scale to large meshes, basically, to be able to capture both long range and short range interactions, and also to be able to generalize to new geometries. So yeah, for one of those models, so there are at least 4 that can solve this problem, this core aerodynamics problem that we have in PhysicsNeMo. But one of them is called Domino. I'm not going to give too much details here, but basically it represents the geometry as a point cloud, and it will basically do some kind of learned projection, and it will learn some nonlinear basis function, and then it's going to pass all of this to a neural operator. So it's a kind of it is a neural operator designed for complex geometries with some. You can see that as a bunch of kind of geometry module. They will process this very complex geometry. They will encode it, and then this is handled by a neural operator. And actually, to have more details, I think you should check the paper that is there. Yeah, so actually this is the name I mentioned before. So actually we have the video. This is what you can use in the web interface right now. So yeah, you can change the velocities, you can remove the mirrors or change the mirrors. There are a few things you can change there. And this is actually using the Domino model, and this is rendered using Omniverse. So yeah. So you can also, it renders also like totally different geometries. So the way it works is that you have those big classes of geometries. So you have the sedan, you have the SUV, and then you can change a bunch of smaller geometrical features on those geometries. And the reason why it's not like an expression of the entire geometrical space, first is because the entire geometrical space is huge. And this is actually the way car manufacturers, car designers work, right? They don't explore the space like in a very wide way. Actually, most of the features of the geometry are imposed by some other aspects, like safety, like the way it looks a lot. And then the CFD engineers, they can only change very few features on the car. So it would be like the wheels, the mirrors, those type of things. So that's the reason why this model is or this NIM, as we call it, is designed in this way with some main classes of vehicles and some smaller features you can tune. All right, so and I mentioned something before, is that those simulations, those AI prediction, those AI surrogates can actually be used to improve classical solvers. So in different ways, but here what the team looked at is using the output of this model, of this domino model, and initializing a transient run simulation, so still for those cars, based on the solution of the AI surrogate. So kind of use that as a kind of rough initial guess, and then make the simulation converge. And actually, in yellow there is the traditional simulation without any kind of smart initialization. The same way that CFD engineer in a car manufacturer company would do it. And in blue, this is the same simulation using the domino initialization. So there is a speed up of times 30. So yeah, that's a kind of nice application of those things, that we can build some kind of hybrid solvers. And you can probably build some more complex stuff, like there are people, they use, for example, when you do multi-physics simulation, where you have a lot of physical phenomena. So I have a background in CFD, so I will talk again about CFD. But let's say for reactive flows, you'll have still the aerodynamics, and in addition, you'll have the chemical reactions. So this is what we call sub-physics. And actually, this is very expensive to solve. So you can also build some kind of hybrid application where you represent the sub-physics by some AI surrogate, and that you plug into your traditional solver. So this is another kind of more, I would say, more. So yeah, it's a bit more involved than this application, but it's another kind of hybrid solver that blends AI and traditional methods. So this is another of those models. So it's always about car aerodynamics because it's a big project in the team, but it can be used really for any complex problem. Actually, we have some open source examples where we apply this to car crash, to reservoir simulation. So in the domain of geophysics, even to more like academic problem, like a deformation of a plate, or like a membrane, those type of things. So this is another of those models that can handle all those complex geometries, and this is called X-mesh graph net. So it's a graph neural network. So it's like a totally different architecture. It's not a neural operator like Domino. And yeah, the way it does is that you see. So the approach of those graph neural nets, the Domino to basically to represent the complex geometry, it does like a kind of where did I put Domino? Can't find Domino. Oh, it's there. You need to do like an encoding of the point cloud, right? And then you pass this to a neural operator. When you do a graph neural network, you don't need to do any of this, because you have your mesh, so your unstructured mesh that anyway you will need for your traditional solver, and you just consider this as a mesh, right? As a graph. So the nodes the nodes of the mesh become nodes in the graph, or vertices in the graph, and so on. So there's a natural structure between like those meshes, those unstructured meshes used in those simulations, and what a graph neural network can process. So there is no need to encode any kind of geometry there. Yeah. Yeah, so this is the XMesh GraphNet. Yeah, some other kind of let's see this one. Oh yeah, this is about physics-informed losses. So everything actually Domino and XMesh GraphNet, the one that I showed before, they are fully data-driven. There is nothing about physics-informed in all of those. So if you want to make those things physics-informed, so this is a stocks flow. So there is an inflow coming from the left side, and you have this object in the middle, and you just solve the flow around those things in the channel there. So it's a kind of a very low speed channel flow, and what you can do on those things is that you just add a term in your training to your loss function, which is the residual of your PD, and then it becomes a kind of a physics-informed model, right? So in the left column, so you see like this is the pressure and the velocities there. The left column is the ground truth. Yeah.
Sorry, just quick question, and you might go into this. So we had two classes previous to yours on where Michael first explained a little bit about pens, and then Pedro talked to us about neural operators, right? In Domino, so the way that you get your data, is it from measurements, or is it you start with the PD, the classical solvers, and then you generate data using those first?
Yeah, you always need to start. I mean, almost everything we do starts from simulations coming from ground truth solver. Yeah.
I see. And then now when you're getting this to physics informed, besides you could have both data and the loss function driven by the PD, right? Sorry. And in this version that you just talked about, when you're saying about putting the residual of the PD, is that like trying to match the gradients or the derivatives?
Yeah, so it's not very smart, right? So you just take your PDE. So in that case, to be like basically so the simplified version of Navier-Stokes, so the Stokes equation, right? So you have your PD, which would be like du over dt is equal to something, right? You just put everything on the left-hand side. You take the MSE of this, and that's the physics-informed loss. So it's really just the residual of the PD.
And then you use AutoDiff to get that for the model, right?
Oh, that's a good point, actually. Okay, so there are different ways. There are a lot of different ways to compute the residual, right? And AutoDiff is one of them. And there is also spectral difference, and there is a finite difference. But anyway, here is finite difference. And actually, it's what so in all our physics-informed modules, especially we usually go for finite difference. Using AutoDiff makes it so it impacts performance a lot. It makes it much more complicated, and the gains are not worth it. They are just not worth it. So usually we just do finite difference. Yeah.
I see, because if you use AutoDiff, then now you have to do higher order gradients on top of that AutoDiff in order to train.
Yeah, then that becomes like a lot of gradients there. Yeah.
I see.
Yeah.
And then you are saying if you use just finite diff to approximate those derivatives, then that's good enough and gives you much better performance in the end.
Yeah.
I see.
Yeah. So what we see there, well, is very obvious, is that all those kind of artifacts there in the flow field and the pressure field, when we have a purely data-driven approach, and just adding the loss actually acts as a kind of regularization term, and we can almost perfectly match the solution. So actually, this is a very interesting I'm not sure if you guys are doing research on this, but this is a very interesting problem, because one of the question we have now, and I think many people in the field have, is that the way we add this physics uniform loss to the data loss is actually very naive, right? We add plus some coefficient multiplied by this loss. We have a kind of we had a kind of weighted version of this loss. And actually, when I say weighted, it's very important, because you can just put like a scalar weight, but actually this doesn't work well if you just put a scalar weight. You could put also a space-dependent weight, right? So in each pixel, you will have a weight that will basically balance between the data loss and the physics uniform loss, right? And you could go even further, because just using space is maybe not enough. Maybe it depends on the actual geometry and the flow features, right? The thing is that probably maybe in the boundary layer there near the angle. Can you see my mouse actually? Yeah.
Yeah. Yes.
Okay. So maybe in the kind of like, like near tip there, near the boundary angle, maybe you want to give more importance to data loss, right? And less importance to physics loss. So there is a lot of tuning that could be done on this coefficient, and there are some kind of orders. Then there is another question, is that should it be a static coefficient, or should you adjust it dynamically during the training? Maybe at the beginning of the training, you need a lot of PD loss, and near the end, you need more data loss. So there are a lot of so actually, it's not clear even. There is not I would say, an accepted consensus about how to. There is not an accepted general solution about what's the best way to incorporate those physics loss into the data loss. So yeah, if you want to do some research on this, it's yeah, I think it's something where it could be very valuable. Okay, so this is actually you saw this example before in the video. It's a data center cooling. I'm not sure if you pay attention to it, but anyway, it's like it's also a CFD problem, a thermal CFD problem, right? And yeah, it's again the effect of adding the physics loss. So if we look at, let's just look at the blue, which is the validation loss without any physics, and the green, which is the validation loss with physics, then we see that we improved by like about 25% of the loss. And so 25% might not seem like a lot, but if you look at the flow features, 25% is actually it's a totally different flow field. You remove all those kind of weird artifacts that you will have in purely data-driven solution. And here the PD loss was kind of easy, but there it's much more complicated, right? You have a thermal flow and a bunch of things there. So the PD is much more involved there. And yeah, again, just going back to the question, this is computed using finite difference, the PD loss. Yeah, this is just a few words about basically how to represent the geometry. That's different ways that we have to represent the geometry in PhysicsNeMo. So actually, PhysicsNeMo can handle arbitrary shapes with the STL format, which is a format for unstructured geometries, for complex geometries. So those are point clouds, and actually they can be converted to sign distance function fields. So sign distance function is basically the distance to the surface, right? You take any point in space, you take the normal to the surface, and this is just the distance. And sign, because like when you're inside the volume, you're -1, and when you're outside, it's +1. So it's a kind of oriented distance. So it's a kind of distance along the oriented normal between the point you consider and the surface of the solid. So, and actually, a sign distance function is actually a complete representation of the geometries, right? It's an implicit representation by a continuous function. It's like you can see that as kind of level set method, kind of level set representation where the level 0 is actually the surface of the geometry. And this actually can be used, the sign distance function can be used to sample points selectively based on the geometry. So the reason why I'm saying that is that before I mentioned maybe you want more points for your, let's say, your PD loss based on the, on how far you're away from the surface, because you have some boundary layers there, so it's how far away you are from the surface. And this you can actually sample the points where you compute the loss, okay, based on the sign distance function, right? So when the sign distance function is small, so when you are closer to your surface, you'll put more points, and then you'll have it's going to result into more weight in the loss for the regions that is close to the surface. Does it make sense or not?
Yeah.
Okay. Yeah. And the sign distance function can be used to go back to the geometry using Marching cubes. So if you use the Marching cubes algorithm, you can just reconstruct the entire mesh of the surface. So yeah, there are a lot of functionalities in PhysicsNeMo to actually that are actually based on the sign distance function and to actually reconstruct the actual geometry. Another area where PhysicsNeMo has some functionality that PyTorch doesn't have, so it's something on top of PyTorch to complement it, is the distributed training. We need to train on multiple GPUs. So there is a very clear difference between distributed training for, let's say, LLMs, and for the distributed training that we encounter usually in science application. So usually for LLMs, the model is very big, right? So one bottleneck is actually the memory footprint of the model. So that's why usually the type of parallelism you see to train LLMs, they are usually based on they will usually start with a model parallelism or pipeline parallelism. So they basically shard the model into different parts. They put different parts of the model on different GPUs, and yeah, that's the type of so then you can add more and more things on top of it to distribute more and more things. You have like tensor parallelism and a bunch of other things, but it usually starts. So it will always start with data parallel. So basically splitting the batch across multiple GPUs, but then can be combined usually with model parallelisms. So that's what LLMs will do usually. But the reason for it is because, in science application, the bottleneck is not the model, because the models we have usually, they are not that big. They will fit on a single GPU. The real challenge for in science application is actually the size of the domain, right? Think of a CFD simulation. You will have like 100 cube. Even a very low resolution will be like 100 cube, right? So this is already like how much is that? 1 million? No. 100 cube. How much is that? No, okay. 100 cube is not a good example. Let's say 1,000 cube. That's a pretty big simulation. That's a billion. That's a volume of size 1 billion that goes into input. And if you compare that to an LLM, where the input is basically a 1D sequence, the size of the domain is multiple orders of magnitude larger for science and engineering application. Just because the domains we deal with, they are 2D or 3D, and they have very high resolution, right? So the type of parallelism we need for science application, so to remove the biggest memory bottleneck, is actually domain parallelism. So instead of splitting the model and putting it across different GPUs, we split the input domain, right? So if you have a mesh of it's what is done actually in most traditional solvers. You have your input mesh. There will be a library like Metis or something that's going to shard your mesh and put different parts of the mesh on different processors. So you actually need the same type of parallelism to train AI surrogates. You need to take the input domain, the input mesh, or all the input field, and to shard them across different processors. So it's a very different thing from traditional parallelism used for L. So that's that's something that PhysicsNeMo supports with a short tensor interface, which is a kind of interface plus plus to the short tensor of PyTorch. And it has also it can also integrate with PyTorch FSDP framework. So it's a fully sharded data parallel to have multi-level parallelism. So you can shard the input domain. You can combine with distributed data parallel, so splitting the batch across different processors, and you can even combine with tensor parallelism and model parallelism. So you can combine all type of different parallelism and basically train on very, very large domain. So that's another feature of PhysicsNeMo. And what you have there are some scaling tests of those. Yeah, there's a question.
Yeah, a fast one. For the domain parallelization, does PhysicsNeMo help you anyway identify how to best do this? I know that it has the capabilities of doing it, but how much is it on the user to predefine how to best do that?
Yeah. We have interfaces that will be the domain decomposition for you. So they will rely on some lower level libraries usually. But yes, it's going. You don't have. You don't have much to do, right? You just call it and it's going to do the domain decomposition for you. I mean, that's the whole point, right? Because if you need to handle those things by yourself, it's kind of annoying. So the most you have to do is to say, okay, we want to split into, the number of shards you want, right? And you can say those shards go. You can even specify those shards go on those specific devices, on those specific GPUs, and it's going to do domain decomposition for you. So you only need to give some kind of high-level information, like how many shards you want, and yeah, which is just usually your number of GPUs that you have available.
Fair point.
So yeah, this was just to show that it scales very well with the number of GPUs. Some quick scale. Yeah, this was I'm not sure this was very interesting, but yeah, this was some kind of validation of those different models for car aerodynamics, but for different quantity of interest, like the Wall shear stress and all those things. So basically, quantity interest that the model is not trained to minimize. Those are kind of a byproduct. So it can also resolve those and it's not like a trivial relationship between this and the actual velocities. So yeah, you can even kind of get good accuracy even on variables that you didn't train for, even on kind of secondary or byproduct variables. Okay, so this is just, I think we're getting to the end of this one. Oh, 31 hour. I was not planning to speak so long anyway. Yeah, so this is a bunch of links and how to get started using PhysicsNeMo. I will put those on the GitHub repo after the session. Yeah, actually, I think like maybe, so I know it mentioned a lot the container. If you actually so container is good if you just want to deploy an application usually. If you want to do development, container not the best environment. But sorry, in that case, you can just use pip. You can just pip install PhysicsNeMo. If you do that on an NVIDIA system, it's just usually going to work just out of the box, right? It will install all dependencies and everything. And actually, if you want to do like more customization, you can even install from source. It's not difficult. You can just clone it and even edit it, do development, the repo, and install it from source. Also with pip, there is not much to do there. So yeah, we'll just go back to conclude on what is PhysicsNeMo. Like, okay, so how to use it and how to contribute to PhysicsNeMo. So I just say there, like I took the same overview, like same like breakdown of what is PhysicsNeMo. That simplifies a lot. Only two main things there: the train recipes and the core framework. So the train recipes, how to use the train recipes? So they are designed to be be hackable. So it's supposed to be easy to hack them. So what it means is that you can copy paste the training recipe and customize it to your own need, to your own. So for example, one of the customization that is the most common is people who just swap the dataset, the training dataset. They will use the same training recipe, but say, I want to apply it to this program, which is almost exactly the same program, but to different dataset. And they will just swap it. Right? This is something very, very easy to do. Another thing that is maybe a bit less common is that I want to experiment a new architecture. So you see, let's say you're doing some benchmark, you develop a newer model architecture, you're doing some benchmark. You want to see if you beat, like, let's say, FNO. Then you take one of those examples you're using FNO, you copy paste the training recipe, you remove the FNO from there, you replace it with your model, and that's it. And same thing for the optimizer and all those things. So this is for reproducible research, right? You can take some source code that was used for research and that was benchmarked. You can replace any parts that you want, for example, some part that you develop or that you want to test. And yeah, that's what the training recipes are for. So it's suitable, yeah, for fast iterations on programs that are not too far from the original program that is targeted by a training recipe, right? You can't use the training recipe and like adapt it to something like totally different. It's not going to work that easily. Then the second thing is the core framework. So those are reusable components that you can import them from PhysicsNeMo and use them into your own applications to build your applications from the ground up. So the very first thing is the model zoo and the data pipes. So both of those are optimized for performance. So if you have a new program you want to, and also something I didn't say, that those things support some level of customization. So you can, for example, import an FNO and you can customize it. So it's not like a hard-coded architecture, right? You can customize some part of it. Just you don't need to re-implement the whole thing. And the parts that are already implemented in PhysicsNeMo are actually optimized for performance. So this would just make your training faster and your inference faster without the need to do it by yourself. And there are other components you can import and reuse. I mentioned the distributed package, in particular the tensor, the domain parallelism with a short tensor. There are a bunch of samplers for different models. So there are a lot of utilities for different models that can be reused just out of the box, basically. Yeah, so this is different from the training recipes. Is to build your own applications or own research code from scratch. Then the third question is how to contribute, because PhysicsNeMo is totally open source. It's not. I mean, it's under a permissive license. So first way to contribute is actually to propose a new training recipe. So basically your last paper, and you just open a PR in PhysicsNeMo. You ping an engineer or a maintainer, and this, at the end of the day, your research, so basically the source code of your paper, will be integrated as a training recipe in PhysicsNeMo. So that benefits a lot the community, and that also benefits you or the person who contributes, because this gives a lot of visibility to the research. Like the example will appear in our documents. It will be clear reference to the paper and link to the paper. So this increases a lot of visibility of the research. And then there are other types of contribution, which would be like to contribute to the framework. So still those two sides there. And this could be a new model. If you develop a new model that is very good at doing something, then it will go into the framework and users can reuse it for their own problem. And it could even be some smaller stuff, like some small bug fixes, some documentation improvement. Any kind of open source contribution is always very welcome, actually. Yeah, so this is a bunch of resources for PhysicsNeMo. Actually, there is a teaching kit that is available online that you can get there. So you will have the link later. So this is Deep Learning Institute training on PhysicsNeMo. So it's how to apply to a few examples. There is actually a part about applying it to weather models. I didn't talk at all about weather models. So it's actually the biggest part of our application. So yeah, there they explain to you how to train models for weather and climate, and how to deploy inference pipeline using Earth Studio. And there is the boot camp, which is also other kind of training. So yeah, to build that where you basically learn to build application using Physics. All right, so that's the end of this part. Is there? So I will need to do something like very complicated. I need to stop sharing and to share the screen on my on my tablet. How can I do that?
So let me ask if people have questions that you want to ask now in this midpoint of the presentation? Prefer to do it after. Okay. Anyone want to do a question now? I have a few questions, but I think I'm going to try to perhaps put them at the end if you think that's better.
No, it's better now, I think.
Yeah.
I guess.
Okay.
Yeah.
All right.
Sorry, how long do we have? Like, I was planning. I don't have a time limit. I'm here until tonight, so.
Some people might have some things to go on, but we have 3 hours of lecture, so you can go as long as you want in theory, because after that also the church deck is at the end, so we'll have this room for as long as we want.
Okay. No, yeah, I think 3 hours is more enough. It's just I was not planning to. I was planning this part to be already 1 hour, but okay. So yeah, we can go for questions now.
Perfect. Okay, I'm gonna start with a general question for you on PhysicsNeMo. What is and all of them are going to be, we have a common theme. What is the best type of application that you can see for PhysicsNeMo? And related, what is the worst type of application that you could try to model on PhysicsNeMo?
Oh, the best type of application. So yeah, so one clarification. What do you mean by best? Like you mean like the one I think is the most valuable, the one I think works well at the moment, or will work better in the future? Like what do you mean exactly by best?
Works well compared to alternatives.
Okay, so yeah, I can give example there. The first type of application that works very well in PhysicsNeMo right now are why is my tablet? Oh, okay. Our weather and climate application. And so there is a simple reason for it, is the availability of data, right? It's not even about the models or whatever. I mean, the field of the field of weather and climate, of AI for weather and climate, is very, very far ahead behind AI in other fields. And this is all due to the availability of data. So, and okay, it's first thing is due to the availability of data, and it's not only about the data exist. It's about all those. So in particular, NOAA in the US and ECMWH in Europe, they invested a lot in the last 15 years to actually build those data sets and to make them open source, to make them open source but easily accessible. So they develop those very high performance file system to access the data and those things. So they have ZAR and those things. So it's not only because when you put 100 terabyte data set sitting on Google Drive, it's very nice, but nobody can ever use it, right? So they develop the entire kind of data infrastructure to actually serve this data to anyone who actually needs them. And it's because those institutions, so those organizations, so they are not companies, they are government institutions. They have spent a lot of time and efforts to actually do it, right? And yeah, like in terms of like CAE engineering, we are nowhere near this level of first of data availability, data existence, even there's not enough data, and data availability in the sense that you can easily pull it from a server and just train on it very quickly. And the second thing is because there is only one Earth, right? So it's very generalized. It's very easy to generalize to new weather patterns, right? Because we have dozens of years recorded, and it's not like there will be like a distribution shift. There is a distribution shift. We know it's like climate change and whatnot, but it's not like a distribution shift between an SUV and a sedan, for car aerodynamics, right? The difficulty of CAE and engineering in general is that there is a very, very, very wide variety of systems. So it's very difficult to pretend that you train like a foundation model that can generalize to a lot of things, because it's the only limit is basically the imagination of a human designers, right? But for weather and climate, it's more constrained. Yeah. So that's why I think weather and climate is it's the one that works the best now. And something I think can work very well in the future is actually anything where the tradition. So you need to look at what is the current solution. Okay, like what is a traditional solver, and if you see some parts of a solver, like some kind of physical phenomena that is very, very expensive to simulate, then I think it's going to be there, that is going to make a difference. Just because the delta between the cost of the traditional solver and the AI model. So the AI model more or less has a constant cost, right? It does not depend on how complex the problem. I mean, of course it depends, but not that much. So if you take like a solver very, very expensive, and you can just generate just enough data to train a surrogate model, then it's a huge gain. Yeah.
Is there, so the both examples that you showed, both the weather model and the DAE, the CAE, with the flow of air or even temperature or tension that you might have on the system that you have, is there something about those problems that make training those AI surrogates very efficient compared to perhaps you can think of an application where training a physics-informed model surrogate being very hard, right? Like to actually get to good performance out of them.
Yeah, that's a good question. So for instance, like those, so I was showing car aerodynamics. So it is most of the stuff we did is on RANs. So it's on steady flows, right? If you go to so now we're starting to move to unsteady flows, to LES, but it's still kind of like the frontier, right? Going for unsteady flows on complex geometries is still yeah, it's like kind of state of the art or kind of ongoing research. Then you can go to more complex flows. Like you see on those, you don't have shock waves, for instance. You don't have like it's just a car, right? It's not an aircraft, for instance. It's not like a fighter jet. It's not a rocket, right? So you can yeah, in terms of it is a complex flow, but in terms of like for example, for me, I have a CFD background. Like car aerodynamics is not the most complex flow you can think of. There are many, many, many more complex flows than this. So yeah, because the flow is kind of smooth. So yeah, that's pretty why it works well for this case as well. You asked me where I think it would be a very bad. Yeah, where it would be a very bad idea to use an ML surrogate. I will go back to what I said, is the delta between the traditional solution. Let's say you have some physical phenomena and you have a GPU accelerated code that can solve the problem in time t with latency t, right? And let's say your AI surrogate can do the same, but t is actually quite small, it's quite fast. And then your AI surrogate will give you a gain of 10% or 20% or 25%. Then it's not worth it. Like those are very, very bad problem to apply machine learning. Like there are a lot of papers, like they show, oh yeah, we train neural networks to do that, and they show like a 2D 70 by 70 resolution domain, something like that. But the thing is that if you run the traditional solver, it will run on a smartphone. You don't even need a GPU to do it. So this is kind of yeah. yeah, those are not good applications of AI surrogates.
Okay, one more question here from our.
I have a follow-up question regarding that. I'm an electrical engineer. So when I was first looking at PhysicsNeMo, I was looking for like electric waves or something like that, examples. And I couldn't easily find anything. Do you think it's because the flow is somehow like way too complicated, or you don't have many applications? What do you think?
So sorry, what do you work on exactly?
I apply electric fields to kill cancer. So
Oh,
I
that's
work
very
with
interesting.
electric field distribution inside the body.
So basically, you solve like in your problems you use some kind of electromagnetic solver. You solve for Maxwell equation, those type of things, or the. Okay, I see.
Maybe.
Yeah. No, I can reply to you actually. So the simple answer is because we are only 10 engineers in the team, and our time is limited, right? So of course,
Okay.
if we had the opportunity to do it, we would love to do it. And I mean, so it's not because it's more complicated. No, that's just not the case. Actually, we do have applications. They are not open sourced yet, where we solve for like the electric potential and those things. It's not for medical application. It's more like in materials, in like semiconductors. But it's definitely a field where work can be done. And actually, if you have, I will bounce back on what I said before. If you have a paper or you did research on that and you want to contribute to PhysicsNeMo, you can just put this or ask us to put this in the examples in the train recipes, because we would love to have those type of applications.
Okay, thank you.
All right. I think we can go for the next part of the talk, and then we'll leave some of the questions for after.
Yeah. Let me see. I need to find my notes. Oh yeah, okay. So I say, okay, I will do, what time is it? Okay, I will be talking, or at least like writing down some random stuff about a graph neural network. Like, but one thing first, are you guys familiar with with graphs in general?
Yep.
Do you use like do you use graphs in your research? Have you ever used graph neural networks or?
I think some of us have, maybe not all, but we have some familiarity with graphs. I think everyone should have some at least.
Okay, that's good then. Well, I will go quickly then on to like yeah, just first just a general introduction on graphs. So let's see. Start. All right, so first. I don't have the best handwriting, but I hope it's more as clear. Okay, good. So yeah, what is a graph? Graph G is a set of vertices that we call also nodes sometimes, and edges. Right. So those are the edges. So basically the connectivity of the graph. Yeah. Oh. Oh. And actually, there is no constraint that that the closest edges are like the closest nodes are linked by edges. So yeah, there could be different things there. So yeah. Okay. So the question is like the first question is, why do we need graphs? So something I said before is that for all those CA problem, what engineers industry do or are used to do is to take those measures. So they are actually people, their job is just to build meshes, right? And they build meshes and then they put it into their solver. So usually their meshes, they are unstructured meshes. I know that there are methods using structure grids combined with some oak tree methods, or some kind of there are some kind of immersed boundary method, those type of things, or cut cell methods. So it's basically some tricks to still be able to use Cartesian grids, but the majority of people in the industry or for industrial problem are used to use unstructured meshes. So the thing is that if you have an unstructured mesh, it can directly become a graph, right? The nodes of the mesh become the nodes of the graph, and the edges of the mesh becomes the edges of the graph. There's really a one-to-one correspondence there. The problem is that, yeah, there is a problem there, is that usually those, they have 10 million to 100 million, sometimes 1 billion nodes, right? And in terms of, so the way to handle graphs in terms of data modality with machine learning is to use graph neural network, right? And so GNNs. And the difficulty there is that it's difficult to scale to so many nodes using the GNNs. Right. So I will be talking about yeah, I will be talking about a specific type of graph neural network that we basically have an entire family of those models in PhysicsNeMo. It's called mesh graph nets. I'm not sure if you guys are familiar with mesh graph nets.
Oh, yeah. No.
Okay, that's good. I can teach you something finally. Okay. Okay, so a mesh graph net. And actually, we have a documentation page in the PhysicsNeMo docs. I will also link it on GitHub after. So it's like it's basically an introduction to this family of model, the mesh graph nets. So there are three components in a mesh graph net. Actually, you can say four. And the first one I'll put in parentheses because it's not always mentioned. The first one is features embedding. This will be basically the question of how to present the features in a way that the mesh graphnet can process it. Then the actual architecture of the mesh graphnet has three components. It has a node and also an edge processor. Sorry, not a processor. Sorry, a second. Encoder. So it's something that will take those features and then encode them. Then it has a processor And the processor is going to apply message passing, so a specific type of message passing. And I will detail what is message passing later. And a decoder. So usually only on the nodes. So it predicts outputs on the nodes. All right, so then, okay, the first I will describe basically like a, yeah, okay. So what I'm trying to do there is to tell you basically, I don't want just to print you like the mesh GraphNet and tell you, oh, here is mesh GraphNet. It's more like a, like to try to put you in the shoes of like maybe an engineer or researcher who has some data. So you know the modality of the data. So you'll have your nodes, right? You'll know what kind of features you have on your nodes, and you will have you have the edges, or maybe not. Maybe you need to compute the edges by yourself. And the question is more about how to process this data with a mesh GraphNet. So the first step is the feature encoding. So we have those nodes, right? And those edges. Just make one now. And let's start by the node. So we can start by the node features. So there could be different types of features, right? The first type of feature you might think of is maybe those would be like a continuous variable or continuous. The one that you'll almost have is a, I will call it a pos, so the position, which is equal to XYZ. So, or XY if you do a 2D, if you're in 2D. So this is almost, you will always almost have it. How to embed it to something the network can process? Usually this one, you have either nothing to do because those are already continuous variable, or you just pass it through an MLP. Okay, so something I didn't mention is that in a mesh GraphNet, or anyway, in a graph neural network, so let's say you have a, where can I write this? You have a graph. With n nodes. The thing is that all those operations, like the MLP I mentioned there, they consider each node to be as a sample. Okay. So it's not like it's going to take the entire graph, put everything together and then proceed like this. It's going to take each node individually and process it individually. Okay. So it will be like so it will take basically pos, which will have a shape of n3, okay, because you have n nodes, and it's going to pass it through the MLP, and it's going to output something called you can call it HP. So it's like the encoded position, and this will have a size N, and you can call it HP, big HP, or the hidden dimension basically. So right, so you see that the MLP is applied to each node position individually, and actually position is just one of them. You can have actually any kind of continuous features. Like for example, in the CFD example I mentioned before, you'll have the velocity, you'll have the pressure, you have the temperature, you'll have all those things. Those are also those continuous variables. The second type of feature you could have are categorical features. So this could be, for example, I'm looking for an example. Oh, let's say you have two types of fluid. You could assign a label 1 to one type and a label 2 to the other. Let's say that you have some other nodes, they represent a solid object or a boundary. You could assign a label 3 to those. Okay, so those could be the node type or material type. And the way to encode those usually is using a lookup, a learned embedding. So it's like it's basically the NN dot embedding from PyTorch. So it's just basically a lookup table, right? And yeah, this one. So it's like you have X. So this is a categorical feature. So X cat. So it will have a size of N. Let's say one single categorical feature. So it's an integer, and it's going to output. Let's make it simple. Then there's another type of feature. Those could be either continuous or discrete, but they are ordinal feature. And the most common one you can think of. So ordinal means there is a clear order. So usually it's like it would be a 1D feature, but there is a clear order. The easiest one is the time, right? So it could be the physical time, or if you are training, let's say, a diffusion model, it would be the diffusion time step. And so yeah, it's physical time or diffusion time for diffusion models. And for this one, usually you'll not pass it through an MLP. This doesn't work well usually. You will use, and you cannot use a categorical embedding, right? You will use a positional embedding. So the classical one would be a Gaussian Fourier embedding. So this will take your ordinal feature. So for example, the time, and it will output. So it will encode into a vector, and basically for the Gaussian Fourier embedding, this vector is going to be some cos sorry, cos f1 x ORed. So just take the input, and then the same with the sinus function. And the reason why the ordinal feature have to go through this kind of embedding is because this kind of embedding would kind of augment information related to the order of the feature, which an MLP will not do. MLP would just do any kind of a nonlinear transformation. And here the frequencies are sampled according to Gaussian distribution. This means 0 and standard deviation sigma, which is basically a hyperparameter that you need to choose. So yeah, those are how to
Charlie,
yeah.
sorry, I think your iPad stopped syncing to the image.
My iPad stopped syncing. Interesting.
Because the last thing we saw was the beginning of the ordinal features.
Oh really?
Stopped on the physical diff.
Is it still not working?
Yeah, still not.
Interesting. Let's see.
Yeah, maybe if you stop and share again, do you think
Yeah,
it's...
I'll try this. Yes. Let's see. Hmm.
Yeah.
Oh, it's
Now
good.
Yeah,
Why?
now
Okay.
it's working.
That's very strange. Okay. Yeah. Okay. So I was talking about the ordinal features. Where did it stop actually?
We were listening, so we kind of know what you're talking about, but we stopped
Oh.
that when you were writing the diffusion.
Okay. Yeah. So yeah, that's the. Yeah. For example, if you have physical time, yeah, I was saying physical time or diffusion time. It's not diffusion modulus. It's diffusion time there. Yeah, you use goes free embedding, which are this combination of sine and cosine function. Just take the feature, multiply it by a frequency, and form a vector like this. And yeah, those are sampled according to Gaussian distribution. Then the next question is how to combine the features. And easiest one is you concatenate them. So in that case, it's going to give you a hidden dimension, which would be like equal to the embedding size, to the embedding dimension of let's say we only have of the continuous variable plus the embedding size of the categorical feature plus the embedding size of the ordinal features. And this is the easiest one. We see that this number can become quite large, and this can be a problem because if you have many input channels or many input dimension, you need to have even more dimension inside of the neural network. So another option is to do addition. So instead of addition, you just do, I mean, instead of concatenation, you do addition. So in that case, so to do that, you need them to be equal, right? So in that case, the resulting hidden dimension is just equal to all the others. There are also more advanced schemes. For example, for the diffusion time, it can be injected at every layer, or you can say diffusion time or the physical time, right? It doesn't matter. But it can be injected at every layer in the neural network. And this is usually done using adaptive norm layers, so either group norm or layer norm. And the idea is that you will have inside of your neural network, so at every layer of your processor, you are going to have some kind of normalization. So you are going to predict some node features, so HL plus 1 at layer L, which will be equal to some MLP of HL, and we'll have a group norm, for instance, of this thing, and you have an alpha that will depend on the let's say we're embedding the diffusion time, and beta of HT. So alpha and beta are both, they will be both learned function, so usually MLPs of the diffusion of physical time. Okay, so you embed it, you pass it through MLP, and then you re-inject it at every layer. That's another mechanism for basically injecting the feature into the neural network. And yeah, this is mostly used for time usually. Okay, so then what I didn't mention there is okay. Now I didn't mention the edge features. So now let's talk about the edge features. Actually, in many cases, you don't even get the connectivity. You just get the points, right? You just get the nodes, and you need to build your own thing you need to connect to build your own connectivity. All right. In the mesh GraphNet, which I am not talking about yet, the edge features you would have for an edge E UV, where U and V are two nodes, right? The feature for UV will be the distance between U and V. There will be a direction. Direction is just plus or minus 1. It's just so the distance is absolute value, and the direction just gives you just basically direction. So the reason why we do that is just because it works better by separating those two features into two instead of keeping them as one. And there's also sometimes something like a kind of augmentation feature. A lot of time you see like a kind of Gaussian of the distance square over some kind of parameter delta square. You will see this kind of feature also very often. It's kind of like it's like it's still a function of the distance, but it's kind of a augmentation feature. Sometimes it can even replace the distance. So there is something very, very important there, is that we never use never we use the absolute position of the nodes in the edges. Never use and the reason for it is because if you were going to use them in the edges, then when applying the message passing, the model will not be invariant by translation or rotation. So it will not be an equivariant graph neural network, right? So that's why it's important to use the relative distance there. And we could put like XU, XV. If we don't care, we could put them. We could put the absolute values of the location of U and V, but if you want equivariance, you should not put them. Yeah. And then and sometimes, okay, you not always, but sometimes you have the edge type. Edge type is usually is something you also need to figure out by yourself. It does not come with the graph. And for instance, in the let me think, in the mesh graphnet, in the original mesh graphnet, which I'm not going to talk about here, there are two types of edges. They are local edges. So those are edges between nodes of the computational mesh. And they are global edges. So global edges represent, for example, the interaction of the node with some kind of external, for example, some external boundaries, those type of things. Yeah. Sorry, they're not called global edges. They are called, I made a mistake, word edges. So in that case, we'll have two edge types. So it's important to have the edge type there. And actually, in that case, the mesh graphnet processes both kind of categories of edges separately. Okay. So so that's it for encoding the features. Is there any question?
I have one question.
Yeah.
So is the mesh graph in the nodes itself, in the applications you have worked on, what do they represent for are they specific parts of the mesh, each node?
Yeah, that's a good question. So actually, it really depends on the application. Like for CFD application and for the applications for which you have a mesh, okay, the nodes of the graph will actually be the points in the mesh. So they could be the centers of the cells, or like or let's say if you have some a tetrahedral mesh, it should be like basically the angles, right, of each tetrahedron. Or it could be the center. There is no constraint on this, but there is a one-to-one correspondence between the actual computational mesh and the nodes of the mesh graphnet. Then there are other types of application where you deal with you're dealing with a meshless problem, like Lagrangian fluid simulation, right? You're simulating particles, Okay, in that case, each node would be a particle. Yeah, so what the nodes represents is actually dependent on the problem you are looking at. Yeah.
Perfect. Thank you.
It could be yeah, just some kind of numerical features like a computational mesh, or it could be some stuff that actually exists, like some particles or some atoms or some defects or whatever.
So for example,
Yeah.
if I have a robot, could be the links on the robot.
Yeah, exactly. Yeah, exactly. Yeah, so then the next step is the node and an edge encoder. So in that step is actually it's extremely easy. It's just you have your bunch of nodes there. Right? And you have a node encoder, usually just an MLP. You have an edge encoder, usually also just an MLP, nothing crazy. And you just take all your nodes and you feed them as a batch to the encoder. So yeah, it's what I told you before. Everything is so the input, for example, the input to there will be of size n and hn for the hidden feature of the nodes, right? And n is the total number of nodes in the graph, right? And then for the edges, it would be of size e and he for the hidden feature of the edges. And what you get in the end is the same vector of size e, h. So you are actually in the graph neural network. So and we are at layer 1, so it's HC1, and what you get there is a NHN1. Okay, that's what you get there. So this is the node and edge encoder. So basically the nodes, they become batch element for the node encoder, and the edges, they become edge element for the edge encoder. Yeah. And yeah, I'm not sure if so maybe I'll just move to the next step. So yeah, in terms of like how to implement these things. So the main library for graph neural network is a torch geometric. So it's just something built on top of PyTorch. It relies on two main data abstraction. For graphs. So the first abstraction is there's an object called data from torch geometric, and this will represent a graph, a single graph. And it has another kind of abstraction, which is called a batch. And it's still a graph, but so the main difference with PyTorch is that in PyTorch, when you batch some tensors, it's like you add a leading dimension, right? And this becomes your batch dimension. In torch geometric, it will batch all the nodes together as a single graph. So it takes n graphs or sorry b graphs, and it puts them all together into a single graph. But it will have so it will have it will have n nodes, which will be n1 plus nb nodes, right? So that's actually something to know about torch geometry is those two things, and you can still access the graph to which a node belongs using the batch attribute. So yeah, the batch graph will have a you have like a it has an attribute dot batch, and this is the yeah.
Charlie?
Yeah.
That's a good question.
Yeah.
Maybe that's what you're getting at, and you're showing us. In the beginning, when you started talking about mesh graph, you talked about graph neural networks and how originally or they have a difficulty scaling. So when you're now explaining how this is somewhat implemented in the packages that you have developed in the mesh graph, is this the batching part and how this is structured is exactly how you bypass this scaling difficulty?
No, it's not. So this is just some very basic implementation. So yeah, no, I was just giving you some generalities about torch geometric, but it's not at all. I was not planning to describe how we batch how we decompose the domain and those things. I think that will require a little bit more time. So okay, so just to give you a very basic idea, we have these graphs and we decompose them. So basically, some set of nodes will go into one processor, right? Some set of nodes will go into different processors, and it just relies on some halo regions. So there will be some nodes that will be duplicated between the processors. So there is a kind of overlap between the partitions, and those nodes are going to be used to exchange data in the graph. So that's one of the main way that we scale the mesh graphnet. So actually, the original mesh graphnet architecture, which I'm talking about here, is actually it could scale to let's say 10,000 to maybe 100,000 nodes, but it could not scale more than this. And it's by introducing those domain decomposition using those halo of nodes that it could be scaled up to tens of millions of nodes. Yeah.
Can I ask you a question?
Yeah.
So lots of people for GNNs, they show that after a specific number of layers, you see diminishing return because you have over smoothing in the final like outputs, whether you're doing like edge prediction or node prediction. Does this occur for this architecture as well?
Yes. Yeah.
Okay.
All right. So I didn't tell you exactly. Yeah. So yeah, there is something I didn't say is how to compute the connectivity. So here, yeah, actually, we go back to this question of what the nodes represent. So if the nodes represent actually the node of the edges, of the computational graph, of the computational mesh. Sorry. In that case, actually, there is nothing to do, right? Because the computational mesh already have a connectivity. You could recompute it to induce like more neighbors, but it's not usually necessary. If the nodes are, let's say, some particles, which is some discrete particles, which is very often the case. In that case, you have basically two methods to compute the connectivity. The first one would be KNN, K nearest neighbors. Actually, it's something we have in PhysicsNeMo. We have some kind of accelerated KNN routines. And the second option would be basically a ball query, or what we call a ball query, or I think it can be called radius search as well. So it's basically saying all nodes below some threshold are connected, right? So those two things. So the advantage of using the KNN is that so the very expensive part of the graph neural network is message passing. It's when you need to scatter the information across the nodes, right? So it's where the nodes actually exchange information through the edges. So the more edges, the more compute you need to do. Okay, so the advantage of KNN is that the compute cost it remains under control. For example, for the ball query, if you start to connect, and let's say your nodes represent actually particles, the particles can move around. Okay, it's possible that you have some nodes that will be connected to maybe hundreds of other nodes. You'll have a very, very high connectivity density, and in that case, the compute cost can explode, and you might not have a clear way to control the compute cost. So, yeah. But at the same time, the KNN is not like physically grounded. So, for instance, the opposite can happen is that if some nodes become very far apart, if you do KNN, this node will still like exchange information with the others, which might not be something that you want to do. But with the ball query, then this node will become isolated from the others, because if it goes far away and the distance to all other nodes is greater than the threshold you impose, then it has no connectivity at all. It's an isolated node. So yeah, one is maybe more physically grounded, but could be more costly, or at least you can't control the cost. But the other one is the other one is as a control cost, but maybe not as physically grounded. So yeah, those are the two alternatives to compute the connectivity.
Can I ask a question? So in practice, I would imagine if you're representing this physical mesh, right? It might be worth varying that throughout your mesh, right? Like, so in certain parts might be worth having more connectivity, in the other parts. Is that explored somehow?
What is usually done is that you would, in some regions, for example, for some regions of the domain, you will add more nodes. But I'm not sure. Yeah, that's a good idea, actually. I don't think it has been much explored, like varying the connectivity, like spatially, for instance. But yeah, that's a good point. I've never tried myself. I can't reply to you, but that's a good idea. Okay, then yeah, connectivity is computed, and nodes and edges are encoded. And yeah, the second step is the processor. This is the core of the Meshcraft nets, and it's one that uses message passing. So what is message passing first? So there are three operations in message passing. The first one is message computation. So for the message computation, maybe it's better if I'll make one node. So we are going to look at this node, which is going to be U, and those are going to be its neighbors. It has three neighbors. I am not going to make any other node in the graph, and those are the connectivity. So to compute the message, so you are going to look at the message between you and one of its neighbors V. So I'm going to compute. You have some function. So this is at layer L. Okay. This is going to be a learned function, usually an MLP, at least in the Meshcraft nets and MLP. So basically, it's very simple. You take to compute the message on an edge, on this edge, you take the features of both nodes, you take the edge feature, and those are three inputs to a function. And that gives you the message for this edge. The second step is aggregation. So that's where you basically combine all the messages together. So then the aggregated message for a given node, okay, here we're considering U, is going to be some kind of a, so I put a plus because usually it is an addition, but actually it's any aggregation function. So it's for all. So this is all the neighbors of U. So here V1, V2, V3. And we have this kind of aggregation function. I'm just going to aggregate the messages. Yeah, this was the message at layer L. So this kind of aggregation function, it could be a sum, a mean or max, or it could be some kind of it could be anything that is permutation invariant. So if you shuffle the messages, as long as the result is the same, you can use it as an aggregation function. And the third step is the update. And here you take the feature of the node U, the center node we are considering, and we are going to layer 1 plus 1, L plus 1, because now we are the next layer. And you have a phi function, which is an update function. And it's just going to take two input, the current node features at layer L and the aggregated message that you just computed above. So this is a learned update function. So this is very general message passing. Then the question is, for mesh GraphNet, how does it look like? So actually, all the graph neural network, most of them, at least all the convolutional graph neural network, they will kind of fall under this. They all fall in this framework, under this framework. So mesh GraphNet is a specific case where there is a small modification. So for the step 1, which is the message computation, layer L. So it's going to be some MLP. And the MLP is always the same. So you see, in theory, the MLP could be different at every layer. In mesh GraphNet, it's the same at every layer. And it takes the current features of the node at layer L and takes the neighbor of U, of the node U, so the neighbor V, and the edge features. And this is concatenation. So it's like a specific case of this where it's like a specific case of the update I wrote above, where the learned message function is the learned message. The learned message function is an MLP, and to take 3 inputs, you just concatenate them. Then there is the aggregation. Aggregation is just the same thing using a sum. So very simple. And something I didn't precise there is that it does another thing. The mesh GraphNet is that it updates the edge features. So I don't know if you noticed there in the class in the mesh GraphNet, in the kind of traditional message passing, there is no update to the edge features. Here there's an update to so in the mesh GraphNet there is update to the edge features. So it's very simple. It's just you take the edge features and it's a kind of actually a kind of skip connection on the edge feature. So you take the message, you compute it on the edge, right? And you just add it back to the current edge feature. So it's like L plus 1 L. So you update the edge feature at every layer. So that's a bit different from traditional message passing. So you do aggregation with sum, and finally for the updates, it's also a kind of it's a similar update as for the edge. So there is a residual connection. You take the same node input feature and you add an MLP to it. And you take the aggregated message and you add it to this one. So it's a specific case of the update I wrote above again, but with an MLP for the learned update function and concatenation for a mechanism basically to put all the node features together. So yeah, so that's what mesh GraphNet is basically. So this is actually the one I wanted to tell you about. So actually there's another version of mesh GraphNet which is called hybrid mesh GraphNet, and this one actually has 2 sets of edges. The one I mentioned above, it has where is it? It has the local edges and the word edges. So for that one, you will need to. So yeah, there are several variants of this. There is a So this is the traditional engine. There will be the so the what we call the hybrid. So it has a node. Sorry, it has a local and word edges. So traditional NGN, I can give you an example. It can be used for CFD application, for instance. Okay, the nodes don't move. The nodes are fixed. Like car aerodynamics. Hybrid MGN, it's good for problems where you have like deformable bodies and contacts. So you have a mesh, basically, a computational mesh, but the mesh can deform and it can interact with some rigid object, I would say. Okay. So the nodes can move, but they are highly constrained in the way they can move, right? Because they belong to the same mesh. And when you do such simulation, you don't have like the nodes, they are not totally free to move anywhere they want. So yeah. So yeah, could be maybe car crash. This is one application where we use those things, the hybrid MGN. Right. And then there is another version is Lagrangian MGN. So Lagrangian MGN is the same as the traction MGN, but the nodes, they are totally free to move anywhere. So the big difference is that in comparison to the traditional MGN, you need to recompute the connectivity. So basically, when you do a rollout, it's like an autoregressive model. So when you do a rollout, you go to the next time step, your nodes moved, and you have no idea by how much. So you need to recompute the connectivity at every time step. So that's kind of expensive.
So
yeah.
Can I ask a question? So the reason why you like the translation invariance is exactly to keep momentum conservation in those cases there, right?
Yes. Yeah, exactly. Yeah, because so there is first one obvious reason, right? Is that let's say you take your car in the wind tunnel, right? If you translate it in the wind tunnel, so you translate the whole flow, it's still the same wind tunnel, right? And the same thing, if you have a wind tunnel oriented to the west or to the east, it's still the same wind tunnel. This has no influence of what's going on inside. So that's why you want to have those invariants. But I think you're right. I think it's even more important for the Lagrangian and GN there, because the nodes are free to move anywhere, basically. Yeah. Okay. Let's see.
One quick question then. So you presented the mesh graph. One of the applications that you showed, or I don't think Domino was using mesh graph, right?
No, Domino is not a mesh graph net, no.
So it's another type of embedding that you use, and then you learn in that embedding there.
Yeah, exactly. Yeah. So you see, mesh GraphNet is that you don't have any embedding, like so the very complex point when you try to deal with those kind of heuristic geometries is how to represent the geometry, all the complexity of the geometry in such a way that the model will be able to generalize to new geometries. Okay. So with Domino, there is this whole thing. So there are all those kind of geometry operators that will basically learn a kind of latent representation of the geometry, a kind of projection, if you will, of the geometry. For mesh GraphNet, actually, there is nothing to do for the geometry because if you have a complex geometry, the graph already fits the geometry because graph, they are unstructured graphs, so they can just fit the geometry, and there is no geometry encoding to do at all. Yeah. And the reason why actually it generalized to mesh GraphNet can actually generalize to a lot of different geometries because it's something I explained before. It's it might sound like like not a big deal, but it considers, yeah, it's right there. It considers each node of the graph as a sample, as a batch element, basically, right? So all those processor steps, like all this message passing, it's applied on each edge and each node independently of each other, right? So let's say you have a simulation with 1,000 node. No, okay, you have a data set with 10 simulations, each with 1,000 node, okay? If you do a convnet on those things, because convnet detect the whole frame as input, right? Or even an MLP. Maybe you can do an MLP. The MLP will take the whole sequence, the whole flattened image as an input. Then in terms of training, it's like the model has seen 10 samples, right? Because those are 10 simulations. But from the point of view of a graph neural network, and in this case of a mesh graph net, each node is a new sample, right? So in that case, it's like the mesh graph net, they have seen 10,000 samples. And I will go even further, is that you can see that the MLP is actually shared. The MLP is shared between all layers. So it's a bit like it has, if you have like 15 layers, it's a bit like the MLP has seen 150,000 different nodes, right? So it can really extract a lot of information, and it can generalize to many more things after. So actually, I'm not sure I showed this information before, but we showed there are some cases where we train a mesh graph net on so it was the X mesh graph net, the one with all the domain decomposition and so on, and it was fine-tuned. It was trained on some geometries and fine-tuned on totally different geometry, and it could be fine-tuned very easily actually. So I think that shows the model really learned some kind of relevant information from the physics, and it can actually be there is a very strong knowledge transfer from the one geometry to the other. Maybe it will not generalize right away to the geometry, but with a bit of fine-tuning, it's actually quite easy to fine-tune because yeah, they're just good to represent complex geometries. Yeah, I wanted. Oh, it's already 1:30. Oh my god. I'm so sorry. It's very slow.
No, that's good.
Yeah, I wanted to give you. Yeah, I think this was important. I'm thinking of skipping it, but I want you to say this part. Yeah. Okay, so mesh GraphNet, I think everything is clear, right? Oh, I didn't say there is the last step, the decoder. So there is just very simple. You take all your nodes. So once again, all the nodes are batch elements, right? So you take all your nodes. You don't even need to care about the edges anymore. You take all of them and you feed them through a decoder. So once again, just an MLP, nothing crazy. And it takes each node as an individual batch element, right? And then it's going to give you, so that case is going to be, so it's going to give you the output on the node, right? And there you will have a H out, basically the output features on the, so this would be it will give you an output feature on each node. Then if you want, you can let's say if you want to create a global property of the graph, so maybe one or two scalars, like something that take the entire graph as input, then you can, after this, you can use a global pooling from Tor geometric, and this will just basically take all those nodes. So it could be mean, max, or any kind of reduction, basically. So you can apply those global pooling operations. It will take all of those. It will compute the mean of the output feature and give you a 1D, so a single output feature for the entire graph. So yeah, that's just a kind of variance, right? The real mesh graph will give you one output per node. Yeah, I wanted to move to the exercise. I'm not sure we're going to have time to do it, but so that's the way, actually, I think most people, at least in our team, they break down. So very often we have to deal with problems that we have never dealt with. Like, for instance, I can be asked to work on reservoir simulation, even though I know almost nothing about reservoir simulation. I can be asked to work on semiconductor manufacturing, even though I know nothing about semiconductor manufacturing. And what we get usually is just a data set with some kind of a very sparse information, right? So we need to figure out, like, what is the data set, and then build a data pipe, build a model. So there is a way to do those things. So so it's kind of a problem solving breakdown. And the way usually we implement stuff for those things. So the first part is always starts from the data, right? It's you need to have a phase of, like, data exploration. You need to understand what is in the data set and what you are trying to model, and problem statement. Then the thing you want to do is implement a data pipe. And that's actually the thing I want you to talk about. Right. This is the very first step. And then you move to define a model. You need to understand the modality, and yeah, then you define a model, right? And finally, right after, you will write your training loops. You can't start to write a training if you haven't done those two first steps there. Yeah. So in terms of data pipe, actually, yeah, I wanted to give you to talk a bit about this. So yeah, I will make a very simple drawing of a schematic of an HPC cluster. So this will be a node, right? Or yeah, just a node. And we'll have, let's say we have 2 GPUs on the node. So this is a GPU. Right. And we have also, yeah, we have a CPU as well. Okay, I'm going to redo this. It's too small. I have room here. Let's see. And we might have I think most clusters have this now, but we're going to have some NVMEs. So NVMe is basically a disk. So it's an SSD disk that is embedded directly in the node, right? And here we'll have, like, yeah, the file system, the disk. Oh, what is this? Go away. I have something popped up on my screen. I don't know what is this. Yeah. Okay. So this is about the, okay, so this is, I don't write it there, but this is about, I want to say a few words about data pipe design. because I think it's like it's always the thing that you need to do first. And after you understand the data you have and the size of the data you have and what you're dealing with, you need to implement a data pipe. And one important question is, where do you put the data, right? So this is basically our cluster there. We have some interconnect between those things. So for example, for the GPUs, they have, I'm going to use another color for some purple. They are NVLink interconnect. The bandwidth would be about 900 gigabytes per second. This is bandwidth. Between the CPU and the GPU, it can be actually a very different story. You would have, it can go from 64 gigabits per second in the case where they are connected through the PCIe. Or it could be 900 gigabit per second for super chips, like a GB200, for instance. Right? They have a specific type of, so they have NVLink interconnect between the GPU and the CPU to make the transfer much faster. Then if we look at the NVMe, from the CPU to the, sorry, no, it's in the other direction. Doesn't go, I mean, it could be in both. Yeah. So the NVMe, it would be slower, usually around 16 gigabyte per second, right? File system is even slower. Could be 1 to 5 gigabyte per second. And oh yeah, in the GPU, there is something I didn't mention, but in the GPUs, you have the HBM, the high bandwidth memory. So this is what is usually advertised as the RAM. And there you have like so they are all on the same die, right? In the same package. But they are the compute cores and the HBM. And so they are distinct from each other, right? There is some data transfer required between the two. And the transfer between the HBME, so the RAM and the cores, it's it's at least 4 terabytes per second. 4 terabytes per second. All right. So if you'd, okay, the point I'm trying to get to is that when you implement your data pipe, so I assume everyone uses PyTorch. You do something like you need to define a data set basically. You have two things to do. You have an init function, right? And this would just read the data from the disk, from the file, from maybe HDF, maybe NumPy files, maybe text files, I don't know, whatever. And you have another function that you implement is the get item, the thing that actually returns the batches. So the final thing it does is return not the batches, the sample from that set. So the question I'm trying to get to is like here, where, so the first question is, where do you put the data? And here, so in the init, when you create a set, when you read the data, where do you need to put it after you read it? And in the get item, so when you actually return the data, where do you transfer it to? How do you transfer it to or from? Whatever. What type of data transfer we need to do there, and where do you store it there? So Given all those things, do you know where to put the data set? Do you know to answer those two questions?
Not. I'm gonna go on a limb here and give you an answer, but probably it's gonna be very dumb and wrong, right? So whenever I depending on the size of my data set, if I can actually put everything in memory, in a sense.
Which
The
memory?
first thing that sorry?
Which memory? There are multiple memories.
Yeah. I would imagine, so what I very dumbly, I would say in the init, I put in the SSD,
Okay.
right, in the compute mode. And then, sorry?
I always put it in HBM in my last project. Yeah, because IMP data set are very small. Like, so I just put all of them on GPU.
On GPU directly. But I imagine that what is getting at is your data set is big enough. I would put first in SSD to then transfer.
Okay, that's a very good point. How big is your data set usually that you work with?
Yeah, well, the last data set was 10 gigabytes.
Okay, do you know how much HBM you have on the H100?
40 gigabytes? I don't know.
You have 80 gigabytes. Some other versions have 90. And when you move to Blackwell, you have, I think it's 190 gigabyte. So unless you are training like a massive model, right? Actually, in my experience, many data sets for like people work with during their research, like outside of like industry application, like kind of academia research. Actually, the sets are not that big, unless you do like weather application. If you do weather application, you have that set 100 terabytes. So there it becomes like it becomes quite clear that and actually, okay, your strategy is the worst.
Fair point.
No, that's not what I mean. I don't mean to offend you or anything. So actually, I'm not sure who said that, but that was totally right. If you have a small data set and you can accommodate, you put it in the HBM, right? And okay, so because what's going to happen otherwise is that, well, you know what's going to happen. I'm sure you can expect. If you run a profiler, like Nsight profiler, and you'll see, so this is time there. You'll see two things, right? You'll have like two rows. You'll have like here would be some communication going on, okay? And you're going to see some stuff like this. And here will be GPU utilization, okay? And here the GPU is going to be header, and there it's going to be used. This is where you actually do your forward and your backward. And then you'll have those little chunks like this. And they might not be that little, right? So all of there, okay, in those chunks is where the GPU is idle, because the data is being transferred from the NVMe to your CPU and to your you see, it takes a lot of time to do that. So the thing is, so there are two strategies to mitigate that, to avoid having a idle, and I'm not talking like 10% increase, right? It's like you have a very expensive GPU can do a lot of compute, and it's going to stay maybe 30, 40% of the time just doing nothing. Maybe even 50 or 60, right? It can be very, very big. And this is actually a very easy gain. This is very easy to do, right? So there are two strategies. The first one is to put data into memory with the lowest latency. So if possible in the HBM. And the second one is overlapping compute and communication. So for the second point, you don't have many options as a PyTorch user to do it. One option is to use when you call the data loader on your dataset object, you have the prefetch factor. So this is going to to pull your data and to put them where they should be, right? To build the batches, to collect the batches, and to put them where it should be. So this is a parameter to play with, but this is from the data loader point of view. It's not in the data set. Yeah, I think it's called prefetch factor. So but this is in data loader. That's basically the only way you can kind of overlap compute and communication. But for the first one, you can actually do a lot of things. So the best strategy is actually, as what was said, to put everything into the HBM, right? The thing is that you could have. Let's take another color. You could have like okay, so this is your data set, right? You could put your entire data set. So you duplicate the data set twice, right? This is the most simple to do. The only thing it requires is here, when you get, let's say you get a bunch of NumPy arrays from your data set, you create, you convert to torch tensors. With device equal CUDA, right? That's really the only thing to do, and it's very important to that in the init. So then it takes literally one line to do, and then they will directly go into the GPU memory. And in the get item, in that case, what kind of data transfer you have to do? Nothing. There is like those training loops where you have those two device. They don't exist anymore because the data is already on the right device. Then you could go smarter, because here we see that I duplicated the entire dataset in both GPUs. So you could maybe go a bit smarter and, oh, let me see. And basically what you do there is that you only you shard your dataset, right? Usually you will use like DDP. This is what most people use. It's simpler. So on the first GPU, you put half of the dataset, and on the second GPU, you put only the other half. So if you train with 8 GPUs, you can reduce basically the effective size of your dataset per GPU by a factor of 8. So that's a huge win. Actually, as long as we are like below 50 gigabytes maybe or something like this, you can use those methods. Yeah. Then the second.
Is there one question? Yeah. Very naively, why, if my memory fits entirely in one GPU, what is of course, I can imagine the more GPUs you have, the more compute you have, right? But effectively, how is that the situation in which I would prefer to using more GPUs? And is that always the case that more GPUs, faster it goes?
So I think there is a level of strong scaling always. This is very architecture dependent, right? Yeah, you are talking about strong scaling, like you're increasing the compute and the time decreases. I think you will hit a limit very quickly, actually. So I think I have to leave the room at 2. I'm not sure.
You need to leave. That's okay.
Yeah, let's finish this, and well, if they ask me to leave, I will need to leave. Yeah. Usually, because the biggest bottleneck usually is not to go faster. The bottleneck, like to train big models, has always been, and especially for LMs, has always been the memory footprint. So going for more GPUs, the primary motivation was not to go faster. The primary motivation was to be able to train bigger models with bigger batches, and then yeah. To go faster, actually, that's a very good point. I think this will be very dependent on your architecture and your batch size, those type of parameters. But for example, I am working on some smaller data sets, and using 8 GPUs actually does not bring, like, maybe brings 10% speed up in comparison to 1. So yeah, in that case, it doesn't make any sense to use 8 GPUs, but you have a node with 8, so you use 8. Yeah. I'm so sorry, I don't have time to go into the coding exercise, but I think it's like already, is it already 3 hours? Oh, yes. Okay. Yeah. Okay. So if you have questions,
yeah,
I'm being
go ahead.
kicked out. So if you have questions, maybe you can. I will update the the GitHub, and you can ask me any questions there. Basically, directly on the the discussion GitHub, the issue discussion, and yeah. All right.
All right.
Thank you so much.
Thank our speaker. Thank you, Charlie Lee. Thank you very much for taking the time and giving us a 3-hour lecture. That was very nice. And I think we have a lot of stuff to go over. If we do have questions, we'll send you, and I guess that we can either open issues or send you an email directly as well, right?
Yeah, sounds good. Sounds perfect.
Perfect. Thank you very much.
So much.
And see you soon.
See you.
Cheers.
Bye-bye.
So which GitHub is he talking about? The one for the course?
NVIDIA.
Oh,
Let me just stop the.
and just stop recording. What happened for the other class where the recording failed?